Hi guys, this is ELEC142 Problem Sheet 3 Part 2 Solutions. So in this video we're going to solve question 2. So you're given a circuit and it's got two circuit components in parallel. That's the main difference between this sheet and this question and what we've been doing so far. So you're told, given the rules for complex impedances or reactances, we've been calling it up till now, in parallel follow the same rules as resistances in parallel. Find an expression for the current I of t for the circuit in figure 2. So this is our circuit. So we've got a sinusoidal voltage source, as we've had before. The current's going around here. And so what we need to do is we need to find an expression for the current. But we've been given a clue. So we've been told that the complex impedances in parallel follow the same rules as resistance in parallel. So that gives us a hint that if we simplify this part of the circuit to being a single impedance, which we can, then we can find an expression for the current, given that we know the voltage and then we'll have a value for the complex impedance. So this all works upon this part of the lecture notes that you've seen. So when we have two complex impedance components in parallel, they behave the same as resistors. So if we have 1 over the total resistance is equal to 1 over the impedance of each of these components added together. And this is the same as resistors in that if we have just two circuit components, why can't I draw a box today? When we have two circuit components, we can use this simplification of the rule, the same as we did for resistors. So it's the product over the sum. You should be quite familiar with this. If you're not, please go back and look at your rules for how you add resistor chains together. So we're going to use this to simplify our circuit. So step 1, as it always is we're going to convert our voltage into a phasor form and write an expression for the current. So V is equal to 20 because that's our magnitude at an angle of 0 degrees in volts. It's 0 degrees because there's no phase shift term here. I of t we know is going to be a sinusoid and it's going to have some peak magnitude I of m, and it's going to have the same basic function as our voltage source because the current is being produced by this voltage source. So it's cos 10 to the 3 of t, the same as our voltage source, plus some phase shift, which we don't know quite what it is yet, so we're just going to leave that term there. And what we're going to do is we're going to simplify our circuit so it ends up looking a bit more like this. And we can see that to get to this situation, we've replaced our individual circuit components with just a block of complex impedance, same symbol as a resistor. It's going to be the impedance of the resistor, this one here, in parallel, so the two slashes mean it's parallel, with the impedance of the inductor, which is this bit here. So the next part of this question is going to be forming this circuit and finding what this value of the complex impedance is. So let's convert our components from their resistances and their inductances into their complex impedances, which both have the unit of ohms, so we can then directly compare them. So the complex impedance of our resistor is just the same as the resistance. So R is 30 ohms, which converts to a magnitude of 30 at an angle of 0 degrees in ohms. That's good. So far so good. That's simple. Next up, we're going to calculate the complex impedance of our inductor. This is equal to j omega L, where omega is related to the frequency we're operating at, and we're given this up here. So this is the value of omega, it's 10 to the 3. So we're just going to put that value in, and then we're going to put the value of our inductor in here, which is 25 millihenries. Calculate that, and we get a value of J, 25 ohms. This is the rectangular form, and we can then convert that to polar form, which I've done here. So I've just done that on my calculator, and we end up with a magnitude of 25 at an angle of 90 degrees in ohms. The J means that it's along the positive imaginary axis, which is up in this direction if you remember your Argand diagram, and it's got a magnitude of 25. So now we've found the value of ZR and the value of ZL, we can then calculate what the complex impedance is. So we're applying this formula where we've got the sum on top, the product on top and the sum on the bottom. So what I've done is I've just put these values in, and I've put them all in polar form for simplicity to start with, but you'll see as you do this example, if you want to make a small shortcut here, you will see because it's a multiplication on the top, put your answer in polar form on the top, and because it's an addition on the bottom, you can put it straight in rectangular form on the bottom if you want. I've just done this so we can see clearly what's going on. So I've put these values in, which I've just got from up here. Then we're going to convert the bottom to the rectangular form to perform the addition. So I've just done this on my calculator, and we end up with 30 plus 0j for the resistor, plus 0 plus 25j for the inductor. Then you can just perform these multiplication on the top and the addition on the bottom. So this becomes 30 times 25 is 750 at an angle of 0 plus 90 degrees, so that's 90 degrees, and the bottom form is just a rectangular form, so it's 30 plus 0, which is 30, plus 0 plus 25j, which is 25j. So that's what we've got here, so that's our simplified expression. Next up, we need to do another step. We're going to convert the denominator back to polar form to perform the division. So that's what we've done there, just in the calculator. This gives us a magnitude of 39.05 at an angle of 39.8 degrees. So we can then do that division. So it's 750 divided by 39.05 gives us 19.2. And for the angles, it's 90 degrees minus 39.8 degrees, which gives us 50.2 degrees. So this is our expression for the complex impedance of Z in ZR in parallel with ZL, which I've just called ZRL. So in our circuit, we could actually just write this value here. That's what it is. We've found that value. And now we've found that value, we can see that we can just easily apply Ohm's law because we know what our voltage is, we know what our complex impedance is, so now we can find an expression for the current. We're working in phasor form at the moment, so let's solve the phasors, and then final step is to convert this back to time domain to find the expression we were asked for in the question. So that's what we're going to do here. Here we know that I is equal to V over Z. Just put your values in. This is the phasor form of V, which we had at the start of the question, and this is our polar form of our complex impedance ZRL, which we've just calculated. We're just going to perform the phasor division, so it's 20 divided by 19.2, which gives us 1.04, at an angle of 0 minus 50.2, which gives us minus 50.2 degrees. This is in amps, so you should hopefully have that unit there already. But then we go back to our final answer. We're asked for an expression of I of t. So we just look at our phasor form. We can see this is the magnitude, so that's I of Im. Cos 10 to the 3t, that's omega, that doesn't change. We already had that. And we're going to put in our previously unknown phase angle, but we found now that's minus 50.2 degrees in amps. And that's the solution for question 2.